screen record this. Or there's the other class, whatever. So get over to your light and particle behavior page, please. As we learnt, to describe black body radiation, we have to use a theoretical body called a black body. The classical model could not explain the peak and then falling back down to ultraviolet because they had an equipartition of states, which gave rise to infinite amounts of jiggle, which gave an infinite frequency. So yes, the ultraviolet catastrophe. Then Max Planck came along and he did a little bit of a mathematical cop-out. He suggested an N or a H constant. He was expecting it to tend to 0, but it turns out it didn't. So again, this was not a blunder, but basically he found one of the most important physical constants that there is without realizing it. All right, so he got the constant named after him. Now, we're going to learn about that HF equation. But again, let us quickly recall this famous photoelectric effect experiment. The idea is that we're now treating the particles of light as little bullets of packets of energy, and they strike the polished metal, they eject photoelectrons. The photon somehow, a single packet interacts with a single electron, giving it kinetic energy. So the photon had the energy, gave it to the electron. It travels through the circuit. It's measured by a current. You put a backwards voltage to stop that current. When you find the stopping voltage, that is the energy required to stop the most energetic. Because remember, a voltage gives you the maximum energy. Okay? So if I accelerate an electron across a certain potential difference, that's the energy of the most energetic electron. There might be a range, some might be a little bit slower, but V would determine the most energetic. Now, by increasing the intensity, all it was saying is that you're going to have more photoelectrons, but none of them have any more energy. So it was intensity of the light did not determine the energy of the photon. The wave model suggested it would. There was also another suggested observation of the wave model, and that would be that there would be a time delay. With a wave, there would have to be a time delay for the electrons to absorb that energy and then break free. But don't ask me how. They're quick with the stopwatch. They were able to figure out that there wasn't any time delay, that the electrons were ejected instantly. As I said, it should have been dependent on the intensity of light, but it turns out no matter the intensity, no electron had more energy. Okay, there might have been more electrons, but they are all stopped by the same stopping voltage. Okay, and if we go back, the other important graph here, this was the big deal. Okay, so this was the big one with a constant intensity. The larger the frequency of light that was incident upon the polished metal surface, the greater the stopping voltage. Okay, and so that was the first link, that voltage was proportional to frequency. Voltage is a measure of work done on a charge, so you're really looking at the energy of those electrons proportional to the frequency of the light. Yes, Wilson?
Why is the graph plateau on the right side?
Really, this side of the graph doesn't really mean much, because basically a positive voltage would be sort of helping the electrons along. It would be like, here, photoelectrons, go faster. All right, so really, it should be like that, but obviously with a slight forward voltage, it's going to, it should be, this intersection should really appear over here. Don't worry too much about the right-hand side, okay? The important thing is where the x-intercept is showing that they split off. Yes?
So that's virtually the only thing we need to take out from that diagram. The different things show that show that the frequency is proportional to the stopping voltage.
Yep, and the first graph is that it's not proportional to intensity.
Yeah. So
the wave model was the opposite. The wave model said that it should be proportional to intensity and it shouldn't be to frequency. The particle model said, nah, it's the other way around. Okay, so this was the photoelectric effect, was the experiment that supports the particle model. Okay, but please remember, this was done around about the start of the 1900s. Robert Millikan came along and found this guy out in I think it's about 1903. So there was a couple of years there, they didn't know the charge of the electron. So they kind of were, they had to wait till somebody figured it out. In the meantime, this is Einstein's idea. Now Einstein, a good pub quiz question, Einstein got the Nobel Prize in physics for his work on the photoelectric effect. He didn't get it for relativity. Everyone remembers him for special relativity and he actually got his Nobel Prize for this. Here's what he said. We're going to look at energy in joules on our y-axis. So we've got positive energy, we've got negative energy, and we've got zero. Okay? This axis is arbitrary, doesn't matter. I just want to spread some stuff out. Einstein suggested that what you have in an atom, such as the metal that was in the photoelectric effect, is you've got various atoms at different bound states. And the one that's in the lowest negative is the most strongly bound. So possibly maybe the closest to the nucleus in one of those good old S shells. And then this one here at the end is the least bound, or least bound electron. Okay? Now, here's Einstein sort of took the experiment and he was able to figure stuff out. He goes, I know what's happening. In comes a photon with a certain amount of energy. So the energy of your photon. First off, that energy of your photon has to liberate that electron. So I'm going to just highlight here, and we're going to call it phi. That's the energy required to get it out and liberate it. Okay? The remaining energy that the photon has is going to go into kinetic energy of your photoelectron. And that is equal to Q V naught. Okay? Now, just a little bit of add in a definition here. Your work function. Energy required to liberate the least bound electron in a metal. Okay? Now you might already be familiar with work functions. You might have all of these potentials on your poster in chemistry. For example, you might have that Na can go to Na plus an electron, and then it might say plus 2.4 volts. For example, I made that number up. It might not be correct, but that's the energy required, or the times it by EV, 2.4 EV to rip an electron off a sodium atom, the least bound, of course. So, you've seen that. And chemists, it's pretty easy to do that. You dissolve some salt in water, and you do your little electrodes, and you put a volt, and you figure the voltage required to separate your charges. This was known. Chemistry had done this. They had the posters up in 1900 that had all of the work functions of different metals. So that was good. Now, so Einstein said, all right, I think I know what's going on here, guys. I think that the energy of our photon is equal to some constant times the frequency. And that's going to equal the work function plus QV. All right? So you see what I've done? The photoelectric effect said that there's some constant of proportionality to the frequency of the photon. That's the energy. First off, it must liberate, and then the remaining goes to QV naught. Okay? So that's what he says there.
So that first bit's derived from the photoelectric effect?
Yes.
The constant, Planck's constant.
It is. Ah, you just spoiled the end of the story. So that's our kinetic energy, if you can recall. All right. Next, this is so Planck did basically all of the really hard mathematics to explain the blackbody curves, all right? You saw that nasty looking equation, the c squared lambda on blah, 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 1 over e to the power of h, blah, blah, blah. Then, here's where Einstein went, all right, cool, here's what we can do. If I was to write my energy not in joules, but in EV, electron volts. Now let's put frequency in times 10 to the 14 hertz. I'm just getting it in the correct scale here. So, guys, let's put a scale onto this. Let's go 2 up to 10. 2, 4, 6, 8, 10, 12, 14, please. And then let's go up to 8. 2, 4, 6, 8, negative 2, negative 4, negative 6, and negative 8. Okay. Now, here's what... I'm just going to put a dashed line at around about 7-ish. At around about 7... we go between visible light and ultraviolet. That looks pretty cool. Look at that little thick highlighter. Visible light and ultraviolet light. Okay? Now, this is what they did. They varied the frequency of the light and measured the stopping voltage. All right? So they cranked up the frequency, different light, different stopping voltage. And they go dot, 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 dot. So there's their data. Then, ruler comes out and they draw in their line of best fit. Oh dear. Oh, close enough. Lazy, mister. Alright, boom. Alright. And I'll just redraw those dots. I should have drawn the line of best fit first, but no biggie. Okay. Now this could be a metal. For example, let's just go for magnesium. They took polished, shiny silver magnesium, they placed it into the photoelectric effect apparatus, they got varying sources of light, and they measured out V. Now, a couple of things you need to know about. The x-intercept is known as the threshold frequency. Threshold frequency. That's F0. That is the frequency of light below which you would not get any photoelectrons ejected. Okay? Just have a think. If your stopping voltage is 0, then that reverse voltage is sitting there going, oh, I'm not stopping anything. There's no electrons coming at me, so I don't have to put a backwards voltage. So at that frequency, no electrons gained enough quanta of energy to be ejected from the metal. So that's your threshold frequency, above which there would be some ejected electrons. Okay? So you could describe it as the frequency below which nothing occurs, or the frequency above which enter statement occurs. So F0, that's your x-intercept. Then, the y-intercept, down here. The y-intercept is the work function. Let me just go a little bit smaller in... Okay, the work function of the metal. So again, if you extrapolate it back, that's going to tell us how much energy would be required to bump your electrons into the positive required voltage. So have a think. The size, and I've just made this up, so let's just pretend it's 7 EV, all right? That's how much energy we need to get the electron 7 EV, and then any more, it would have to be stopped by a stopping voltage, because then it has some kinetic energy. Okay? So that there is the work function. Now, pardon me, the great thing is, in chemistry, they had numbers for magnesium. Let's pretend that it's 7. And then, empirically, the data suggested All right, so it worked. Like physics agreed with chemistry. The chemists nodded. Yep, you got the right number. They extrapolated it back. Okay. Then next, they said, all right, let's see if this works for other metals, because we know other metals. Let's go potassium. And let's figure out some stuff for potassium. Now, I'm making these numbers up, but could you please draw some dots? And what do you notice about these dots? Exactly, nobody. They're translated vertically downwards. Keep the same gradient. Try and draw in a parallel line. Okay. And same deal. For example, this is suggesting that it's about, 9. And so we go, yes, correct. Chemistry. We go, potassium goes to K1 plus? K plus? Plus 2 EV? What? Plus 1? Why did I write the E there? That should just be 2E negative, 1E negative, bracket 9EV. Okay? So it all agreed. Next. It was at this time that Millikan came along and said, hey, buddies, I found out something that might help you here. Q equals 1.60 times 10 to the negative 19. Joules per coulombs. And they're like, thank you very much. And now our y-axis is energy and the x-axis is frequency. So now we can figure out that constant of proportionality that Planck was talking about. Okay? And so all they needed to do was do a little bit of rise over run. All right. So we'll do our EV over Hertz, which is s to the negative 1. Okay? And there, just down here, if you've got the room, we'll go E equals HF. So therefore, gradient, well, let's just write the word gradient, equals E over F, which equals H, which is known as Planck's constant. Okay? Now, if it's in EV, you do your rise over run, and you get H equals 4.14 times 10 to the negative 15 EV seconds. All right? Because remember, it's EV seconds because we've got EV divided by s to the negative 1. So it's an inverse of an inverse. And so the units are EV seconds. Okay? So this is now the link between frequency of light and the energy of the photon. As the frequency goes up by 1 hertz, the energy that that photon has increases by that amount. But unfortunately, that's not the value that's given in your data sheet. They've given you the value in joule seconds. But that's all right because we know how to convert from an EV to a joules. You could times that to get to joules. And in your data sheet, you have 6.63 times 10 to the negative 34 joule seconds. The unfortunate thing is it's actually easier to work in EV. The EV is a much better unit of energy of small particles. If you're in joules, then you have to use notation times 10 to the negative 18 joules, whereas you could just say it's 0.5 EV. Okay? So we just got to be careful. Moving forward, if you're going to use the EV value, you have to show the conversion from what's given in your data sheet. All right? So just make a note for me, please. In data sheet, not in data sheet. Okay? Oh, look, over the page. We're going to write it again. Oh, man. Wasting paper here. So it's 6.63 times 10 to the negative 4 joule seconds in datasheet This is what I wrote last year. And over here it's 4.14 times 10 to the negative 15 EV seconds. And obviously I said we can convert between the two. Normally you would be going this way, which would be to divide by 1.60, because in your data sheet you got the value and you might want to convert it. Now, there's some cool equations here, and I just want to, again, there's a problem. It rolls off the tongue, it's HC on lambda, but that's not in the data sheet. What you have is Planck's constant, or Planck's law. You've got energy of a photon. Here we go. You've got E equals HF. And then you've got C equals F lambda. All right? So then we could rewrite F equals C on lambda. And we could throw him in, and then you get E equals H times C on lambda. Okay? So all I've done is expressed F as C on lambda. So again, one's in the data sheet. Essentially, if you want to solve for lambda, you could start straight off with this equation and just rearrange for lambda. But really what the data sheet's saying is, well, how about we just do a side mission first, find me the frequency using Planck's value, and then you can use the wave equation to find wavelength. So essentially it's just two equations put into one. So you can do it in one step rather than in two. Okay, but again, just be careful, show all of your working out. So, here, gentlemen, let's figure out the range of energies in EV. Okay? So, for visible light, that's lambda for violet, and that's lambda for red. Okay? So if we've got our visible light spectrum here, doesn't really matter which way you draw it, 700 nanometers to down to about 400 nanometers. And again, depending on which spectrum you use, some books might say, oh, the light spectrum goes down to 380 and up to 720. Others will say 400 to 700. Okay. So on this side we would have infrared, and on this side we would have ultraviolet. And I want you to figure out what the energies of the boundaries of those two are. So let's just for now use our E equals HC on lambda. Now, since it's asking for energy in EV, that basically means you use Planck's constant in EV. You could use the joules, but then you would have to convert your energy at the end. So you could find the energy in joules and then convert, or you could convert Planck's constant at the start, and then the energy comes out in EV. All right? Practice will make perfect. There's plenty of questions that we can use. Can I just do that and then do that? Yes, that's better. So, 4.14 by 10 to the negative 15. Speed of light. Divide by its wavelength, 700. If you haven't already been told by me at some stage in your education, use this lovely button. Use the fraction button here, gentlemen, because we've got lots of brackets, lots of indexes, lots of numbers. We're dividing, we're multiplying. So make sure you use that fraction button. It'll reduce the risk of making a mistake. We get around about 1.77 EV, which, if we wish to convert, okay, so those are your energies in joules and in EV. Could you do the same for me in the next couple of minutes? Do the same for ultraviolet, please. Okay. Do that for me now. Find me the most energetic photon of visible light and the least energetic photon of visible light that our eyeballs can see. How? Are we missing anyone today? Alright, thank you. I'm going to do attendance. So guys, 3-mark question, equation, working, answer. Yep.
Is it alright if we don't give the, in terms of like getting all the marks, can we just put it like straight in like HC times by 1 on the peak, 1 of the wavelengths minus 1 on 1 of the wavelengths?
So really, if this was a test, that's not in your data sheet, and neither is that. Alright, so I'd spend an extra 10 seconds just going, like your torque, right? Sum of all torques equals 0. Yeah. I'd go E equals HF, F equals C on lambda, therefore E equals HC on lambda. Done. You've shown the marker where that equation came from. Then I would go Planck's constant equals 6.63 blah 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 divided by 1.60 times 10 to the negative 19. Okay. At some stage, you have to divide, well, here we times by, but at some stage you'd have to do the conversion. Okay? Yeah, so give it, let me just write it all in. 4.14, 10 to the negative 15. All right, what energy do we get? Awesome. Or 498, yeah? 497. Oh. So, here is why you might be able to see it's a lot easier to remember these nice rounded numbers than some ugly notation. Okay? So, this is, again, these values are not in your data sheet, but these are good numbers that I want you to be able to recall, because you might be given a photon of light that has 4 eV of energy. Straight away, I know that it's going to be in ultraviolet, because the energy caps out for visible, it caps out at about 3.1. Beyond that, if your eyeball got smacked by a 4 eV photon, it wouldn't send an electrical impulse to your brain and you wouldn't perceive it as light. It might damage the back of your retina because now it's ionizing. Okay? This would explain, for most molecules, beyond violet, it's now considered ionizing. I teach my year 9s and I teach my year 10s that ultraviolet and X-ray and gamma rays have enough energy that when they flick that electron off, the electron disappears and you turn your atom into an ion. Okay? So obviously this equation E equals HF, which is not on the board, is now supporting that as frequency goes up, the energy of the photons goes up. Okay? Which is why they can do a dose of radiation. So just on this little scale here, if I can write it correctly, infrared is therefore less than 1.77, and ultraviolet is greater than, you know what I'm trying to write. Okay? So a good, again, yeah. Oh man. Yes. There we go. Generally, sometimes, often, a question will give you photons of light that might be around about the visible light. And so if you can just remember those numbers, again, it's a little check. You can check, I'm pretty sure I've got the right answer because I've got a value that's a little bit higher than 4 or a little bit less than 1.7. Okay? Now, what else have I scribbled down? Oh, for some reason, I asked for green. let's go our Roy G. Biv. So, Roy G. Biv. I have a green laser pointer. I've got two now because Mr. Masterson confiscated one. Don't bring green laser pointers to school, they get confiscated. 512 nanometers. Okay. Fine for me. Now, straight away, if this was a question in a test, right? Hey, Mr. Murray confiscated a 512 nanometer green laser pointer, calculate the energies of the photons. I know it's going to have to be between 1.77 and 3.11 because we're pretty much smack bang in the middle of the visible light spectrum. So now, if you make a mistake and you times instead of divide, or you put 14 instead of 15, your number, if you make a mistake, then you're checking yourself. So, quick little maths. Last question for me. Work out the energy of our photon. Go, 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 go. 2.43. Sounds good. Sounds correct. That is the answer, and I just want to see what questions we've got. Do I want to force you to do questions yet, or can I show you some cool videos? Hang on. Oh, you will have homework to do. Yeah, some good stuff. What was that? What was that noise? Some sort of bell ringing. Okay. Cool. Just remember, guys, Planck's constant is a physical constant. It is constant. It is constant. It is the same here. The other side, it's consistent. So remember, we've got permeativity, permeability in the data sheet. It's the electric and magnetic constant. You've got the speed of light, which is a constant, but really, in a vacuum, it's 1 over the square root of that times that. You've got the gravitational constant, and now we've got Planck's constant. There might be a couple more that I can't recall at the moment, but these do not change, or at least we think that they are the same. And there's some cool, obviously, people that are smarter than I have said, if any of these constants were changed ever so slightly, then the world we exist in would be very different. So if Planck's constant was slightly bigger or smaller, then things would look different colours. If the permeativity or permeability was different, then light would travel, magnetism wouldn't work the way it does, gravity. So we're quite lucky that these constants are the way they are, or maybe we've evolved in the constants so that we could survive. And if the constants were different, we might have 5 arms and 3 eyeballs. Okay, nice philosophical question to think about there. Now, I think I'll stop talking and I want to show you a video. I've got no idea if I'm playing it too soon, but it's a Veritasium video on well, I don't have it written down, so I'll stop the recording and I'll find it.